In these, we can find certain common characteristics. One of the most apparent is disorder, as can be seen in this channel flow. The disorder is of such a fundamental nature that the flow never is reproducible in detail, no matter how carefully one attempts to reproduce all the boundary conditions. Although the details are not reproducible, averages over suitably large intervals of space or time may be very well defined and stable. Disorder, then, is a necessary factor in any definition of turbulence. It is not, however, sufficient. Here's a pretty disordered fluid motion, but it would be unwise to include it in turbulence. A wave field like this does very little mixing, and mixing is an essential feature of turbulent motion. The mixing action of turbulence can lead to complete blending if the volume is confined, or to the dilution, which is the only thing that makes pollution like this or this fairly tolerable. Another characteristic of turbulence is the presence of vorticity. In a turbulent field, the vorticity is distributed continuously but irregularly, and in all three dimensions. So turbulent flow has more than one distinguishing characteristic or symptom. Perhaps we can borrow the word syndrome from pathology and say that we have a defining syndrome or set of symptoms for turbulence. These are disorder, irreproducible in detail, efficient mixing, and vorticity, irregularly distributed in three dimensions. This definition effectively isolates turbulence from various kinds of wave motion. It also eliminates all two-dimensional flows. Something roughly like turbulent motion can exist in two dimensions. Weather systems on a large scale represent nearly two-dimensional flows. However, the characteristics of such flows are in many ways so different that it is perhaps unwise to include them in turbulence. Some flows, like this jet, are clearly turbulent.
Okay, so I thought I'll show this video because honestly I have never seen anyone do a better job of introducing turbulence than this guy. Okay, so and no one has the swagger of lighting up a cigar in middle of a lecture. So as you saw that there are three essential characteristics of turbulence, and even experts like him are not comfortable defining a turbulence. Okay, they are saying you can identify some syndromes of turbulence or some characteristic features of turbulence, that is if a flow exhibits those three particular characteristics, that is irregular distribution of vorticity, mixing, and what was the third one? What was those three? Disordered motion. Okay, so chaotic in a very general sense. If these three characteristics exist, then you are safe to classify the fluid flow as a turbulent flow. Okay, so the idea behind turbulent flows is something which follows our which follows the way we have been doing and analyzing flows in this course, and that is you have a laminar flow. Okay, you have a laminar flow. Let us say, he will show an example also. You have a laminar flow. If this laminar flow is, let us say, linearly unstable, okay, linearly unstable, then you will see that the perturbations grow in time, and after some time you will see turbulence ensue inside the flow. What this means is that after some times it becomes almost impossible to track these perturbations in a very deterministic sense. For example, in instability, what we did was, once we substituted the normal mode assumption, let us say something like this in your shear flow. Okay, once we substituted our normal mode assumptions, let's just look at, okay, kx plus kxx plus kzz minus omega t. Once we did this, we were looking at a particular triplet, let us say, or pair in 2D. We were looking at a particular triplet of omega kx and kz. What that means is we were looking at a one single mode or each of those single modes and seeing how they grow in time without interacting with each other. The interactions of these modes are captured only by nonlinearities. Okay, you can think of it something like this. Let us say I give you a governing equation that looks like this. Okay, so this is not something very different from Navier-Stokes equation, but let us say I give you a governing equation like this, and I say that the initial condition of the flow of this flow variable u is sine x. Okay, so you will see that u del u by del x is basically sine x times cos x. Okay, and this non-linear term is what brings in the interaction of different modes. If ux comma 0 was sin x plus sin 2x plus sin 3x, then you would see multiplication of the modes here, and it's the multiplication of the modes that represents the interaction of the modes with each other. And by nature of linearization of governing equations, we dropped that multiplication. Okay, the moment we said that we are going to understand things from linearized equations, we dropped any multiplications of these modes. Okay, any multiplications that we had in our linearized system were of the base flow and perturbations. We never had perturbations times perturbations. Okay, and in turbulence, those are the essential ingredients, because they capture the essence of turbulence, which is the intermodal interaction. And after that modal interaction or intermodal interaction, what happens is, in this region, which is usually called the transition region, it is very hard to track individual modes. Okay, but in transition region you may be able to still track, let us say, 10 or 15 of the modes that are occurring, but in turbulence it is almost a hopeless job. And so while most of the this regime of flows can be studied deterministically, so deterministically analyzed, a very suitable process of analyzing turbulence is statistical analysis. Okay, and some of the people who made very long lasting and very impactful discoveries in turbulence were actually statisticians by profession. Okay, A.N. Kolmogorov, who gave the first underlying universal theory of turbulence, was actually someone who formalized probability theory. I don't know if you guys have taken a course in probability theory, but to define a random variable, you basically need a measure, a Borel set, and sigma algebra, and so on and so forth. That formalization, that mathematical formalization, was actually given by Kolmogorov. Before then, probability was introduced by coin tosses. Okay, and he made a very important discovery in turbulent flows. So turbulence by nature, it is deterministic, but it is our human ignorance that makes it impossible to be tracked deterministically. It is something very similar to atomistic systems. Since you guys are doing multi-scale modeling, in an atomic system you can model it. So if you guys have seen molecular dynamics, you can model an atomistic system by Newton's second law of motion. Okay, every molecule, if you do not consider any quantum interactions or anything, every molecule you can give you can describe its motion by f equals ma. Okay, but if you have a large system of molecules, okay, let us say you have 1 mole of molecules, then you end up with how many degrees of freedom? So if you have order 10 to the power 23 molecules, for each molecule you have a, so if you are writing d 2x by dt square equals f of x, so you have x and x dot as degrees of freedom. You have positions and velocity as degrees of freedom. So you have 6 degrees of freedom for each molecule. Okay, 6 into 10 to the power 23 is the number of variables that you're going to have to track once you consider a 1 mole of substance. Nearly impossible. Okay, hence you deal with it in a statistical fashion. You develop statistical mechanics, you look at the ensembles, you look at microcanonical ensembles, and so forth. Turbulence is not something very different. Okay, there are some peculiar differences between turbulence and statistical mechanics of molecules, but by and large, if you look at it from a very zoomed out perspective, turbulence is not so different, and analysis of turbulence mandates statistical analysis. Okay, something like this that you are seeing, this is a turbulent jet. The jet flow that we have looked at in our laminar flow analysis, when we basically solved for boundary layers, that jet flow basically doesn't even exist in this regime, in this picture that is shown. What happens is you have a jet that is coming out, and very soon there are instabilities that happen here and things become turbulent. Here it is very difficult. So if I draw this line and I plot velocity on this line, you will see that the velocity fluctuates a lot. Okay, and it is very difficult to reproduce that velocity fluctuation every time you do the experiment. There will be some perturbations from the atmosphere, some things which will make the reproducibility of the flow nearly impossible. Okay, and that is turbulence.
Others are equally clearly not. What is it that determines whether or not a flow is turbulent? To help answer this question, we'll use this apparatus, which is a version of that used by Hagen over 125 years ago in the study of flow through pipes. In these two tanks, we have two different glycerin water mixtures. One mixture has viscosity about 3 times that of the other. The valve permits us to obtain any combination of the two mixtures. The fluid is pumped by this constant displacement pump, so that the flow rate remains the same no matter how the mixing valve is set. Our pipe begins here. Midway down the pipe, we start a manometer tube, which we carry downstream so that we can see the upstream pressure simultaneously with the end of the tube, where the pressure is atmospheric. The manometer reading will give us a measure of the average pressure gradient along the tube. Now we start the pump. The manometer reads about 10 units. Now I change the valve setting to reduce the viscosity. As the low viscosity fluid flows into the pipe, the manometer reading decreases.
So this is very intuitive. If you have less viscous fluid that is flowing through the pipe, basically the pressure losses are less. Okay, that's what manometer reading is showing you. Okay, what is the pressure loss across a given length? So when he decreased the viscosity, the pressure drop decreased. Okay, but see, as he keeps decreasing the viscosity, what happens?
Once more I change the valve setting to still lower viscosity. Once more I change the valve setting to still lower viscosity. But look here. We have increased the pressure difference, which means that we've increased the drag. Let's look at it again. I increase the viscosity.
Now notice how the flow looks here.
And down goes the pressure difference. I decrease it again. Up it goes. Now, let us look at the fluid coming out of the end of this pipe. Notice that the fluid comes out in quite a smooth stream. We have the intermediate viscosity with its corresponding low pressure difference. Now let's go to the lower viscosity with the high pressure gradient. The edges of the stream coming out of the tube have become blurred. If we look at this stream in slow motion, we can see that the blurring is resolved into an irregular motion of the surface. The flow has become turbulent, and the onset of turbulence in the pipe has revealed itself both in the irregular motion of the fluid stream and in the greatly increased drag in the tube. In the early 1880s, Osborne Reynolds did a series of experiments on flow-through tubes and came to the conclusion that the criterion for the onset of turbulence was a dimensionless function of the flow parameters, which has since been called the Reynolds number. There is usually a certain amount of arbitrariness in the definition of a Reynolds number, but for pipe flow, let's take it as the diameter multiplied by the average speed divided by the kinematic viscosity. Although the question is still under investigation, it seems that if the Reynolds number, so defined, is appreciably less than 2,000, the fluid is not turbulent. In this experiment, we have deliberately made the input conditions somewhat abrupt. Turbulence occurs at a Reynolds number not much over 2,000. However, if we improve the entrance conditions by putting a nicely flared funnel at the upstream end, we can delay the transition to turbulence to a much higher Reynolds number. Now we have increased the flow rate and further decreased the viscosity. With very great care, it is possible to push the Reynolds number up as high as nearly 100,000 without turbulence. However, here we can reach only about 8,000. The onset of turbulence depends upon the growth of perturbations because of an instability. For example, at this Reynolds number, the flow alternates between laminar and turbulent modes, apparently randomly, depending, presumably, on some random variations of the perturbations. Prominent in our defining syndrome was the word mixing. What about mixing? Let's modify our experiment by introducing a thin streamer of dye into the flow.
So please focus here. This is very
Notice
important.
that the dye forms a thin filament which maintains its identity with very little change right down the tube. The only mixing is molecular, and the concentration gradients are so small that this process is very slow. This is laminar flow. Now we increase the Reynolds number. At the onset of turbulence, our dye filament seems to explode, and the dye is rapidly mixed across the tube. If we want to, we can regard the increase in pressure difference as a manifestation of mixing too.
So the idea here is that, as he shows, that once you have a dye that is being injected into this pipe, when the flow Reynolds number was small, there was hardly any mixing of this dye filament. Okay, when he says that the only mixing that you see is molecular, that means this dye is some concentration. The concentration is governed by, let us say, this equation, the standard convection diffusion equation. So there is some diffusion of the dye. Okay, there is some smudging of the dye that is happening as you move downstream, but that is all molecular. Okay, but what happens, because this diffusivity, this is due to molecular nature of the dye. But as you increase the Reynolds number, what happens is this dye, as you keep moving downstream, it gets these instability and eventually gets mixed through. Okay, and this mixing, why is this mixing happening? Because if you zoom in inside the turbulent flows, what you will see is that the flow velocity is not a very nicely defined parabolic profile that you guys have been seeing. It is very irregular. Okay, it will be very irregular, and there will be some average that you can define for this velocity. We will come to the averages, question of averages in a minute. And so the idea is that there is a mean flow. Okay, there is a mean flow or the average flow, and on top of that there are some random perturbations, or as they are called, eddies, which exist. And what these eddies are trying to do is, basically, as you have an eddy like this, so this eddy is not just rotating at its place, it is moving or getting convected down with the mean flow as well. And what is happening is, as it keeps doing this, it transfers some momentum to here and some momentum from here to here. So the job of this eddy is to take all the fluid properties with itself and redistribute them with more effectiveness. So that's why you see more mixing in a turbulent flow than laminar flows. In laminar flows, the only transport of properties that is being done is through molecules. Okay, why does viscosity or any kind of molecular diffusivity exist? If you look at a plane in a space, and let us say you focus on the molecular nature of the matter, so what happens is there is a mean flow of these molecules due to macroscopic flow, and there are some random thermal vibrations. Due to these random thermal vibrations, some of the molecules, let us say, will cross this plane, okay, and they will carry their mean momentum with themselves as they cross the plane. And as a result of this carrying of mean momentum across the plane, you will see that there is a diffusion of mean momentum across the plane, and that is your viscosity. In turbulence, along with molecules, small little eddies and vortices play that role, and they do the job much more effectively than molecules, because molecules are so small in size they can only operate at very small length scales, but eddies can be of very different length scales. Okay, molecules can be of order of, let's say, nanometers or angstroms. Eddies could be of orders of millimeters to meters depending on your flow setup size. Okay, so those eddies are redistributing momentum, temperature, concentration, any inhomogeneity you can think about, and trying to make it as much homogeneous as possible. And as he is about to say, that due to this redistribution of properties, you also see large momentum mixing. So momentum mixing, what it means is that if you look at laminar flow, through pipe, you have this parabolic profile. There is a very huge difference in momentum at this location and at this location. What eddies try to do is they try to deposit this momentum here, they try to deposit this momentum here. So on an average, the velocity profile for a turbulent flow that you will see will look something like this. It will have a more uniform nature, and close to the walls it will have very steep gradients. And what do these steep gradients close to the wall mean? The du by dy at the wall is large. If the du by dy is large on an average, so let us say we denote an average with this type of an operator, angular brackets. So let us say this is your velocity average. So let us say this is your du dy average. So if this guy is large, then this guy is large. So your shear stress in the case of a turbulent flow is much larger compared to a laminar flow because of this mixing of momentum. The eddies are trying to diffuse the momentum much more rapidly than what molecular diffusion could do or viscosity could do. They're trying to take, because of their rotational nature, they're trying to bring this high momentum at the low momentum region and vice versa. Okay, and so due to this, you see a large gradient, and the large gradient manifests itself as a high pressure drop in a turbulent flow.
Momentum. In laminar pipe flow, the velocity profile is parabolic. Near the wall, there is a considerable quantity of relatively slowly moving fluid. Dye injected near the wall marks some slowly moving fluid. When it leaves the pipe, it falls with a steep trajectory. Notice that the slowly moving fluid near the top of the pipe also falls steeply.
So you see, this is a very nice demonstration of the fact that flow near the walls is moving slowly compared to the core of the flow. Okay, when he injects dye close to here and here, the dye can be seen along this stream, which has a smaller range because the velocity is smaller at which it is starting. But when he'll inject the dye here, you will see right at the center, when he injects the dye stream almost goes to the outermost stream as it comes out. So right now he's injecting at the top and it flows down here.
The rapidly moving fluid from the middle of the tube falls on a flat trajectory.
See? So the dye is coming from the middle and it is going all the way. Look at that.
Compared with laminar flow, that turbulent flow, the mixing of momentum causes the velocity to be much more nearly uniform. The fastest fluid is not quite so fast, and there is very little slowly moving fluid. What little there is can be dragged along with the rest when it leaves the pipe. Nevertheless, the velocity must vanish at the wall, so we can regard the wall as a sink for momentum. Turbulence increases the rate at which momentum is transferred toward the wall. Thus, with turbulence, we need a larger pressure gradient to replace the momentum lost to the wall. Although the principal motion of these bubble patches is downstream, there is a very appreciable cross-stream component. Fluid moving across the stream in this way tends to carry its properties with it. It is these cross-stream velocities which do the mixing. For example, the momentum close to the wall is appreciably less than that in the center of the stream. The cross-stream motion carries low momentum fluid into the center of the stream and high momentum fluid toward the wall.
So this is exactly what I was telling you here, that the slow moving fluid is not so slow and the fast moving fluid is not so fast, okay, due to this cross mixing caused by the eddies. Now the question that arrives is, what is the nature of these eddies? Okay, when we talk about these so called eddies of turbulent flow, what is the nature of these eddies? That is, do they have some bias in the motion, or are they isotropic in nature? That is, the eddies have no directional dependence and they could exist in any direction given a statistical realization. So if you draw anything from this sample of a turbulent flow, you are equally likely to see an eddy with any direction vorticity. And the answer is that it depends on the setups, of course. And so the nature of these eddies is something like this. So let us say you have this again turbulent pipe flow, okay, and at this point you have a pitot probe, and you plotted the velocity recorded by the pitot probe. Let's say this is a 3-point probe, so it can measure x, y and z velocities, so u, v, w. In a laminar flow you will see something like this, 0 and 0. This is what you will see in a laminar flow. Now in a turbulent flow, the velocity measured by this probe in the x direction will look something like this, okay, and the velocity in y and z direction will also have some fluctuations. And it is the mean, of the y direction velocity which will be 0, it is the mean of the z direction velocity which will be 0, and the mean of the x direction velocity will be some, let us say, u bar. And from here you will say that the turbulent flow is, let us say you see this is not changing in time, you will say that the turbulent flow is steady and one unidirectional. The turbulent flow, the moment you say that it is a turbulent flow that is steady and unidirectional, you are not saying that the velocities exist in only x, y, z, in only x direction and y, z are 0. What you are saying is, you are accepting the nature of unsteadiness in turbulence, you are accepting the nature of 3-dimensionality in turbulence, and what you are saying is that on an average the perturbations in other directions will cancel out and you will only be left with this. So whenever I say there is a flow that is unidirectional and steady, and the other thing is I say a turbulent flow which is unidirectional and steady, they both carry different meanings mathematically. Okay, in a turbulent flow that is unidirectional and steady, the velocity you cannot say is so du by dt you cannot say is 0, and neither you can say that v and w are 0 in a steady unidirectional turbulent flow. It is the means that obey these properties. Okay. Now the question of means begs the question, what kind of averages that we are talking about. For example, if you look at this kind of a flow, the x axis here is time, the way you will evaluate these averages is basically you will sample it at multiple times, and you will say, oh, this average is basically 1 by n sigma I equal to 1 to n, where different realizations were obtained at different times, where these different realizations were obtained at different times. This is basically called a time average. Okay. What you could also do is you could obtain the velocity at different locations. You could put pitot probes at very different locations. Okay. At a lot of different locations, you could put the pitot probe. Okay. You could define an average. Let us say, let me denote it like this. So, the time average I will write like this, the spatial average which I am going to define, I will write like this, and here you will say that these are different realizations in space. Okay. This is spatial average. Now, the other average that you could take is the standard averages that you learn about in statistics and probability theory, and that is you perform the same experiment multiple times. Let us say you perform the same experiment n times and you measure the velocity of the fluid at the exact same time after starting the experiment at the exact same spatial location. Okay. So, if I write it more carefully, the time average, this is basically 1 by n sigma I equal to 1 to n u at a given spatial location at different times. Okay. This one, if I write it more carefully, this is 1 by n I equal to 1 to n. It is u at a given time and at different spatial locations. The other average that I am talking about is an average which is done over multiple experiments. So, basically it is at a given location at a given time over multiple experiments, and this is called an ensemble average. You do multiple experiments. Hundreds of you, let's say, if they ever show up in class, they are doing 100 versions of the same experiment. Let us say a pipe flow, and they start an experiment at the same time, let us say t0, and they measure the velocity at the same location in their respective pipes after 10 seconds, let us say. So, that is what I mean by the same spatial location at the same time, and then we take those 100 readings and we make an average out of them. So, for example, let us say you guys did AMP 262, right. So, if you take an average of a reading right when you are doing the experiment, you are most probably doing this. Okay. But let us say I ask you to take one single reading after 10 seconds, and I ask all the batches to do that, and then I collect their readings and take an average, then I am doing this. Okay. So, these are the three different averages that you can actually calculate in your turbulent flows. There are some class of flows which are steady turbulent flows. Let us say in a steady turbulent flow, what you will see is that an ensemble average is equal to the time average. Okay. And this is very similar to the thermodynamic equilibrium properties of matter, in which what you say is that if a matter is in equilibrium, or if turbulence, let us say, is in equilibrium, then while it is evolving, turbulence is in equilibrium, turbulence is steady. That does not mean all the velocity profiles are steady. Velocities are still unsteady. Turbulence being steady means that this guy, the ensemble average, is independent of the time where when you take the average. Okay. So, what it means is that you could take it at different times and you will end up with the same value. So if you take averages of different same if you take averages of the same value, you will get the same value. So that's why ensemble average will be time average. Okay. No, because I'm saying that the turbulence is steady. Steadiness of turbulence doesn't mean the velocity is ordered. What it means is that over a longer period of time, the turbulent, so let us say you observe an experiment for a very long period of time. Okay, let's say you observe it for 1 month, and let us say you take a lot of experiments and you observe them over short intervals of time. The idea of steadiness of turbulence is that you will observe some form of what you have observed in your short time experiments at some point in the long term experiment. In mathematical sense, what it means is, let us think about it in terms of a phase space diagram of a dynamical system. Basically, let us say pendulum x and x dot. Forget about pendulum being deterministic. Let us say gravity and all of those things are statistical in nature. The idea here is that as the system goes about in its phase space, it will have visited all of its probable phase states. So that means if it has visited all of its probable phase states, that means if you conducted a different experiment, there are high chances you would observe a phase state which was already observed in the long time dependent system. Okay, and this is called Poincare's theorem, where what he said is that for a nonlinear system which is steady in equilibrium, basically the ensemble average is actually equal to the time average. To be specific, what we say is that the ensemble average is equal to time average when this is tending to infinity. That is, this ensemble average is 1 by, let us say, t 0 to t 0 to capital T, limit t tends to infinity. This is also called ergodic theorem. And the idea of ergodic theorem is that when you have a stationary turbulent flow or a turbulent flow which is in equilibrium, thermodynamically equilibrium, not equilibrium in the sense of F1 plus F2 equals 0. Okay, thermodynamic equilibrium and dynamic equilibrium are very different things. Okay, thermodynamic turbulent flow is in equilibrium, or you can think of it like steady turbulent flow. Then what I'm saying is that the ensemble average is equal to a very long time average. Okay, and based on this formulation, Reynolds, who did the same experiment and after whom Reynolds number is defined, he proposed a decomposition of velocity fields as something like this. This is called your Reynolds decomposition. Not just velocity fields, of pressure fields as well. So according to him, you have this decomposition, you can do a decomposition like this for velocity and pressure fields. Okay, what you can say is my velocity, my turbulent velocity at some point of time, at any point of time, is this ensemble average plus a turbulent perturbation. Okay, and by definition of this relation, if you take this, if you are looking at steady flows, then this holds. So integration sign will commute over addition and you will get an average of the average, something that is already constant. Even if you integrate it over a very long period of time, it will still remain that value, and this will be basically, and by definition of this, what you get is that the perturbations on an average, the mean of perturbations is 0. The mean of perturbations is 0. Now, in the similar fashion, let us look at a product of two variables and let us look at the mean of that. So, let us say we look at p times u. I know it doesn't exist in your momentum equation for incompressible flows, but let's just for the sake of discussion, let us look at P times U. What do you get? P plus P prime times U plus U prime. Yeah, this and then like this. So this will give you mean of P, mean of U plus P prime mean of U plus mean of P times U prime plus U prime P prime. What is the, so integration? So this is integration for steady turbulent flows. Integration commutes. So I can write it like this, and then I can write this like this. This quantity is an average of product of averages. Both if you are multiplying two averages, then if you just look at time average, they are not functions of time. You have integrated time out, and since this is a steady flow, time average is equal to the ensemble average. So this is nothing but this. What about this? Here mean of U is not a function of time anymore. So this is nothing but mean of U times mean of P prime. Similarly, this guy is mean of P times mean of U prime, and this guy we cannot break this apart. When is an average of product of two things equal to the product of averages? When is that? When does that hold? When do we say expectation value of x times y is ex times ey? What is the condition? Independent. You cannot generally say that P prime and U prime are statistically independent. So you cannot do anything with this term. Okay, without making some very blatant assumptions, you cannot do any simplification here. And by definition, mean of P prime is 0. By definition of mean of U prime is 0. And so you end up with mean of PU is basically mean of P times mean of U plus mean of P prime U prime. Okay, and it's these kind of terms which make analysis of turbulent flows very hard. Okay, when we try to determine these terms, as you will see when we derive Reynolds average, Navier-Stokes equations, you will see that average of average of two multiplied terms depends on triple multiplications, average of triple multiplied terms depend on 4 multiplications, average of 4 multiplied terms depend on 5 multiplications, and basically there is no way to obtain this from an average equation. There is no way to obtain this from an average equation. So very unfortunately, there is no governing equation, a closed governing equation that we can give for an average velocity. There has to be a term which has to be modeled or found out somewhere from someplace else. It is very similar to, basically, if you think about it, let's say you have matter made up of molecules. Molecules are obeying F equals ma equations. Are these F equals ma equations reversible in time or not? What do we mean by reversibility in time? If I swap t with minus t, the equation stays the same. Basically, for a reversible system, you could not say if it is moving forward in time. Let us say I record a video of a molecule going in time. You will not be able to tell if it's a real molecule or not if I play the video forward or backward. That's what reversibility in time means. But if I give you, let us say a block of some metal, and I heat it at some point, and I keep it cooled at other point, and I show you, let us say I can show you the temperature and velocity movement of all the molecules and so on and so forth, you will be able to tell if the video is moving forward in time or backward in time, because going forward in time temperature will diffuse, going backward in time the temperature will segregate, which is counterintuitive. Temperature doesn't segregate, entropy cannot spontaneously decrease. Entropy can only spontaneously increase by second law of thermodynamics. So there is an irreversibility in the system that is composed of a large number of reversible systems. There is an irreversibility in the system that is composed of a large number of reversible systems, and the same thing appears in turbulent flows. There is an irreversibility that is added by these products. Even though you have governing equations for these perturbations, very obviously you can substitute this kind of a decomposition in a Navier-Stokes equation and obtain the equations, but you cannot obtain a closed form equation for the average of these perturbations. Average is something where, average is something that you observe when you observe a very large number of reversible systems. Okay, that is the average behavior that you are seeing. So on an average, these large number of reversible systems show an irreversibility, which you cannot model, which you cannot obtain mathematically from a large number of reversible systems. In fact, this is still a challenge in statistical thermodynamics, that oh, I have a system of a large number of reversible systems, how the hell does it become time irreversible? Okay, this is a standing problem in statistical thermodynamics, and it appears in turbulence as well, that just the fact of observing a large number of system means you're observing averages. So the thing is that you cannot govern averages, you cannot find a closed system that governs averages just from considering the constituents of those averages. You have to model somehow, you have to model the behavior of those product terms and things like that. Okay, and we'll try to look at this Reynolds average Navier-Stokes equation in our next lecture. I suggest you watch this movie and other movies of these fluid mechanics films, because there may be some problems that appear in your major exam inspired from them.